Sorry for the separate video, my computer died. So let's just talk about problems for density. So we're talking about density. Remember, density is equal to mass divided by volume. And so we're going to do a few problems with that. And so I think I'm on 2 problems if you're keeping notes. And the first problem is, what is the density of a sample if the mass is 5.72 grams and the volume is 8.321 milliliters? That's an M, milliliters. So starting this question, we have our equation, density equals mass over volume. And so go into the question and figure out what things are given to us. What is given to us? Right here, mass is equal to 5.72 grams. What else is given? Volume is equal to 8.321 milliliters. What is it that we're looking for? What is the density? Right? So that's what we're trying to solve for. So this one's pretty straightforward because we were given mass and we're given volume, so we can just take these 2 values and plug them into our equation. Density will be equal to 5.72 grams divided by 8.321 milliliters. And if you punch that into your calculator, 0.687417, maybe some more digits, our units will be grams per milliliter. And now we have to worry about sig figs. So when we're looking at sig figs, 5.72 is 3 sig figs, and 8.321 is 4 sig figs. This lets us know we can have in our final answer 3 sig figs, right? Going by multiplication division rules. Also remember that beginning zeros do not count. So that 6 is our first significant figure, 8 is our second, 7 is our third. We can only have 3, so we're going to cut the number there. We're dropping a 4, so do not round up. So I'm going to round that to 3 significant figures to be 0.687, and my units will be grams per milliliter. When you're working on these problems at home or you're writing them out to turn in, please be sure to always check your sig figs and also ensure you have units with your answers. Okay, so let's try a second problem. Problem B. What is the mass of 10.7 cubic centimeters of aluminum given the density is 2.7 grams per cubic centimeter? So again, this is a density problem. So we're going to use density equals mass over volume. And now we have to figure out what is given to us. So starting out, just reading through the question, if you want to, it says, what is the mass? So mass is what we're looking for, right? Masses are unknown. And we have this, we have 10.7 cubic centimeters. What is 10.7 cubic centimeters? Well, it doesn't give you exactly what it is. So you have to look at the unit. This is a unit of volume. And so we know then that volume must be 10.7 cubic centimeters. So it didn't say what is the mass of a volume of 10.7. It just gave you 10.7. And then what else is given to us? We have a density of 2.7 grams per cubic centimeters. So in this problem, we're given volume and density, and we have to solve for mass. So you can kind of think about this algebraically. If you're trying to solve for mass, you have to get that on one side of the equation by itself. So to do that, I'm going to multiply this side by volume and this side by volume. So I'll have volume times density is equal to mass. Now I know my volume and I know my density, so I can just go ahead and plug them in. 10.7 cubic centimeters times 2.7 grams per cubic centimeter is going to be equal to my mass. Cubic centimeters will cancel, and I'm going to end up with mass units of grams, which means that I did everything correctly. If I punch this into my calculator, I believe I get 2.889. You might get some more. Units will be grams. Now let's check on sig figs. This is 3 sig figs, 10.7. 2.7 is only 2 sig figs. So my final answer can have should be 2 sig figs. So I'm going to keep the 2, I'm going to keep the 8, I'm dropping an 8, I'm dropping a number that's greater than 5, so I got to round up. So my final answer would be 29 grams. Again, don't forget to include your units. If it turned out that the volume was given to you in 1 unit, say centimeters cubed, and the density was given to you not in centimeters cubed, you'd have to follow what we did in the previous chapter and convert units. You'd have to make sure that whatever volume units you put in here are the same as the volume units for your density. If these 2 units are not the same, then you would have to go ahead and do conversions in order to get them to be the same. We'll try some of those in lab and in our group meeting. So let's try one last problem. Problem C. What is the volume of 15.55 grams of aluminum? Again, the density of aluminum is 2.7 grams per cubic centimeter. Again, we're using density as mass over volume. And what's given, and what do we have to find? What is the volume? So volume is our unknown. That's what we're trying to solve for. We have 15.55 grams. What is gram units for? Gram is a unit of mass. And so I know my mass is going to be 15.55 grams. And then my density is given to me again, 2.7 grams per cubic centimeter. So what do I do to solve this? Now this one's a little bit trickier algebraically, and this is the one that most people don't really follow through the algebra correctly. We're trying to solve for volume, but right now volume is on the bottom of the equation. So the first thing we have to do is get volume out of the denominator and up onto the numerator. So I'm going to multiply both sides by volume. I'm going to have volume times density is equal to mass. Now again, remember I want to get volume by itself, so I'm going to divide by density, and I'm going to divide by density. So volume will be equal to mass over density. I know my mass and I know my density, so I can go ahead and plug them in. 15.55 grams divided by 2.7 grams per cubic centimeter, right? That's my density, that's my mass. And what's going to happen? Gram over gram is going to cancel. What happens to my cubic centimeters? It's not 1 over cubic centimeters. It's actually going to come out to be centimeters cubed on the top. This is as if we took 1 divided by 1 over x, right? If you divide by a fraction, what do? Invert and multiply. So this would be the same as 1 times x over 1. So this is the same as 1 over centimeters cubed. Right? So centimeters cubed is going to come to the top just like x would come to the top. Numerically, 15.55 divided by 2.7, you get a number of 5.75925, maybe some more digits. Again, follow sig figs. 4 sig figs and 15.55, 2 sig figs and 2.7, so my final answer should have 2 sig figs. So I'm going to keep the 5, I'm going to keep the 7, I'm going to drop a 5, round up. So this is going to be 5.8 centimeters cubed as my final answer. So we'll work more on density in a lab to get you going with that. But those are some of the types of equations that you should certainly be able to go through, work through, and solve. The last thing I just wanted to talk about on this segment, and then we'll break to a new video so it doesn't get too long, is I also want to talk about the states of matter. And so within the states of matter, I believe almost everybody knows, right, that there are solids, there are liquids, and there are gases. We're not going to talk about plasmas. We're just going to stick with the 3 basic states of matter: solid, liquids, and gases. And so what are some characteristics of solid, liquids, and gases? How do you know by looking at something whether it's a solid, liquid, or gas? If you're have a bottle of water with you, how do you know that the water inside that bottle is liquid? How do you know that air is a gas? And if you have the bottle itself, how do you know that plastic is solid? What things about solids tell you that they're solid? Well, the most common way to know that something is a solid is that it has a definite shape. This is the characteristics of solids that distinguish it from liquids and gases. Both liquids and gases have indefinite shapes, which means that they can change shapes, or they change their shape to fit the container that you put them in. So if I measure out a cup of water and I move it from the measuring cup to a bowl, it doesn't hold the shape of a measuring cup. If I have a sugar cube and I take a sugar cube and I move it from the container into a cup, it's going to still be a cube because that's a solid. Gases will take on whatever shape you allow them to have as well. So the number one way to know a solid is that it has a definite shape. Now, how can you distinguish between a liquid and a gas? Well, the difference between a liquid and a gas is that liquids have a definite volume, whereas gases have an indefinite volume. What does that mean? If I measure 1 cup of water and I take that 1 cup of water and I pour every last drop of it into a bowl, how much water is in that bowl? 1 cup. If I take that cup of water and I throw it across the room and it's scattered everywhere on the floor, if I could scoop it all back up, it would still be 1 cup of water. But if I had a cup of, say, propane gas in my hand in some way, or in a cup container with a lid on it, it would be a cup. If I open the container, what would happen to that gas? Would it stay in the cup? No, the gas will start expanding and spread out. So gases will take on whatever shape their container is, and gases will take on whatever volume their container is. And if you don't have gas in a container, it will keep expanding across the atmosphere. And so just for completion's sake, if solid has a definite shape, it must also have a definite volume. It can't change its volume if it can't change its shape. Now, there's some other things about solid, liquids, and gases that I would like to add in here. One thing is that solids are typically non-compressible. That means that you can't push the particles any closer. If you apply pressure to them, they're not going to change their volume. Liquids are slightly compressible. You can get a liquid, and if you squeeze on it hard enough, you can compress it. And actually, if you compress it enough, the liquid will become a solid. Gases are highly compressible. Now, why would this be true? This is true because in a solid, the particles are very close together. In a liquid, they're slightly farther apart. And in gases, they're very far apart. And so if they're very far apart and you apply pressure, you can squeeze them together. If you apply pressure to a liquid, you can smush them a little bit closer, but if you apply pressure to a solid, they're already as close as they're going to get, so they're not going to get any closer. So there's some other things about their motion. Why is there a definite shape for solids? It's because the particles cannot really move around. They can't translate in space. Particles can only vibrate about a fixed point. So I'm not saying that the particles aren't moving, but they're not moving in space. So they can sit, like if you were on your chair and fidgeting, that would be vibrating in a fixed position, but you can't get up out of your chair and walk across the room. Solids can vibrate in a given space, but they're not going to move their space around. Liquids have more freedom of motion. And gases, if they're ideal, which we'll talk about later, have total freedom of motion. Gases are pretty typically moving in straight lines in random directions until they collide, until a collision occurs. When they collide either with another gas particles or with the walls of a container, that can change their direction. But They're also moving very quickly. And we'll talk about how quickly in a later chapter. When you have a liquid, liquids have more freedom of motion than solids. That's why they can change their shape, but they can't change their volume. So it would kind of be like if you had particles that were liquids, particles that were solids. Solids would be very close together, liquids would be further apart. But what would be true is this distance between the particles is always going to be held. So if this particle moved over to here and went away from being here, my overall volume cannot change. So it would kind of be like if you had a room full of people and we were attached by, say, ropes that were 2 feet long. People could move around, but you have to keep the ropes spread at 2 feet all the time. You could change the overall shape of what all of the people, the area that we all took up, but you wouldn't be able to just have a person leave completely. In solids, everybody's just sitting there and nobody's really going anywhere. In gases, the particles are really far apart, further than I can draw on this. And what's true is if this one moves over there, nobody cares because they're so far apart, they don't really have any interactions, which leads me to the last thing. Particles are highly attracted to each other. In a liquid, particles are less attracted to each other. And in gases, if it's ideal, we say there are no attractions between particles. So to just give you a better visual of solid, liquids, and gases, I just want to try to share with you a quick little simulation. Oh. So if we look at this simulation, this is neon in the solid phase. If I look at it in the liquid phase, see how it occupies more space? The particles are further apart. Again, look at, there's the solid, here's the liquid, and watch what happens if I look at it as a gas. Particles are much further apart. This is true not just of neon. If we look at other substances as well, if we looked at oxygen, here's oxygen as a gas. Here's oxygen as a liquid. Here's oxygen as a solid. So again, if I'm looking at things solid, close together, and they're vibrating, liquids, they're further apart and have more freedom of motion. Sometimes 1 or 2 escape, like this guy going up to the top, that's evaporation. And if you have a gas, they're much further apart and they're moving much more rapidly. So you should be familiar with solids, liquids, and gases, and you should be able to predict what things are solid, liquids, and gases. So we'll have some practice with that in our group activity as we move forward in the course. The last thing that I wanted to talk about in this particular video is physical versus chemical. And I think I'm on C. And this is just a quick intro. We talk about chemical and physical properties of matter, and we talk about chemical and physical changes of matter. And so if I had an ice cube, which is solid water, and I melt it, and I turn it into liquid water, what kind of change is that? Is that change a physical change, or is that change a chemical change? Well, the difference is, if it's physical, there is no change in the identity of the substance. If it's chemical, the identity changes. Or you could say a new substance, new and meaning a different, right? Not like never discovered. A new substance is formed. So with that piece of information, what do you think? An ice cube melts. An ice cube is water, H2O. Liquid water is H2O. Did it change its identity? No. So therefore, when you melt things, this is a physical change. Any change in the state of matter is going to be a physical change. All changes in states of matter are physical for any given substance, because it's never changing what this thing is, it's just changing how far apart the particles are and how they're moving. So that would be an example of a physical change. What happens if we had a piece of iron? And so in here we have all these iron atoms, and I leave it out in my backyard over 6 months. What's going to happen to that piece of iron outside for 6 months? It's going to rust. So what do you think? Is rusting going to be a chemical change, or is rusting going to be a physical change? Well, to begin with, iron, whoops. Iron has different appearance, right? Iron is silver in color, whereas when it turns rust, it gets kind of orangey color. That's because rust is actually a different substance. Rust is actually iron oxide. Rust is, oh, actually, I just drew iron 3 oxide. Iron 3 oxide. So it's a new substance. This is just iron. It's changed its identity. If it changes its identity, it is a chemical change. Now, I know this is kind of challenging for you to do right now because we haven't really talked about chemical formulas. So you don't have to be an expert at this for right now, but I'm just hopeful that you can get the key concept and think about chemical versus physical changes. So let me just try one other one with you. Say I was trying to make a cheap, quick version of a grilled cheese sandwich. And so I toast bread in my toaster, and then I put cheese on it, and then I put that under my broiler in my oven to try to just melt the cheese. And I wait for a little while and the cheese just melts, and so I pull it out and it's just kind of soft cheese. Chemical or physical? Think about that for a minute. I leave it in my oven and I forget about it, and I open it up and my oven is billowing with smoke and the cheese is all charred and is now black on top. Chemical or physical? So the question is the melted cheese, when it's just melted, still cheese? The answer, yes. Melting that cheese is just physical. Burning the cheese, chemical. That black substance that's formed on the top, that charred piece of it, is actually carbon. It's changed from being cheese to just being carbon. So we're going to come back to this idea of chemical versus physical. And I didn't really talk about the properties, but properties follow the same thing. If measuring the property does not change the identity, then it's physical. The key is changing the identity. If the measuring the property does change the identity, then it is chemical. So rusting is a chemical process. Burning is a chemical process. To say that cheese can burn, that is a chemical property. To say that iron rusts, that is a chemical property. Rusting is a chemical change. So it's kind of a little bit of semantics in the language, and we'll practice more as we go through and have more substances to work with. So that's it for this segment. Hope you're all doing well.